Good morning, everyone. It's just after 10 a.m., so we're going to go ahead and get started here. Thanks for joining us for today's webinar. I'm Signe Lerfall. I'm the coordinator for the Northern Rockies Fire Science Network. In case you're unfamiliar with the network, we're one of 15 regional fire science exchanges that are funded by the Joint Fire Science Program. The Northern Rockies Fire Science Network delivers science and provides opportunities for engagement between managers and scientists about important fire and fuels topics in the region. To learn more, please visit our website at nrfirescience.org. On behalf of our team and our partners, I want to welcome you to today's webinar, Learning a New Way to Sample Wildland Fuel Loadings, the Photoload Technique, presented by Dr. Robert Keane. Just a couple of housekeeping items before we get started. All of the attendees are in listen-only mode for the whole webinar, but you can ask questions of me or our presenter at any time by typing them into the question or chat pane of the webinar control panel. These questions will help facilitate discussion following the presentation. Whatever you do in the control panel does not affect the presentation, so feel free to type a test message or test your audio at any time. And a recording of this webinar will be available on the Northern Rockies Fire Science Network website and YouTube channel soon after the conclusion of the live webinar. All of you will receive an email with a link to the recording once it's available and any additional resources. So with logistics out of the way, I'll move on with introducing our presenter. Bob Keane has been a research ecologist with the USDA Forest Service Rocky Mountain Research Station at the Missoula Fire Sciences Lab since 1994. His most recent research includes developing ecological computer simulation models for exploring landscape fire and climate dynamics, conducting basic research in wildland fuel science, and investigating the ecology and restoration of whitebark pine. Bob has had a long and storied career and will soon be retiring, so we're very lucky to have him here today. Thanks a lot, Bob, for being here, and you can go ahead and begin the webinar whenever you're ready.
Okay, thanks, Sig. Appreciate that. Hello, everybody. Welcome to the day after President's Day. I guess this would be called Vice President's Day. And what I'd like to do today is talk about a new sampling technique. Actually, it's not new. It's over 10 years old now, but people are starting to pick it up and use it, and they're finding some real success with this method. If you're anything like me, you've probably done miles and miles. I've done over 100 miles of Brown's transects, planar intercept transects over across various stands across the Northern Rockies. And if you were anything like me as well, you'd start to notice that I wonder really if these planar intercepts have really given us accurate fuel loadings. So about 15 years ago, a team out here at the Fire Lab delved into this and found out that, you know what, Brown's transects were not really probably that accurate for doing fuel inventories, especially at a plot and stand level. Brown's transects were originally developed to populate fire behavior fuel models, and they were really never, in order to use them to get a really accurate inventory of wildland fuels out there, you really had to put a lot of transects in. So, so many transects that it would have become almost impractical. So, what to go ahead and use besides Brown's transects? Well, today I'm gonna talk about that. I'm gonna talk about the four main sampling techniques that we use to sample wildland fuels, and then I'm going to introduce the Photoload sampling technique and allow you to do it. One of the big things I think that the Photoload technique gives you is the fact that you're constantly visually cued to the amount of fuel that are out there. And let's see if anybody is cued out there. Take a wild guess in your mind of how much fuel, how much 100-hour fuel is in this 1 by 1 meter box. How about if I gave you this, pick an A, B, C, and D? How much fuel is there? Probably half of you are saying, I have no idea. The other half are going through all of them. And then finally, they would come up with the answer is 20 tons per acre. Now, this is the problem with Brown's transects, is that when you do the actual counts on the planar intercept transects, you never ever get an idea how much fuel is out there. Whereas many other fuel sampling techniques also don't allow that. Whereas the Photoload technique allows you to calibrate your eye to real world conditions so that you can then not only estimate fuels accurately, but you can do it at multiple scales. So with that, I'd like to start the background on why we develop photoloads. Well, first of all, as I said, bounce transects were developed really to create fire behavior fuel models to put in the Behave program, or Rothermos spread model. And, you know, most of you know that those fuel models aren't really accurate depictions of wildland fuel loadings. They're just loadings that have been keyed or changed so that they'll give you the right fire behavior. Well, in today's world, we really need to predict fire effects, and we need actual accurate fuel loadings in order to do that. And we need the fuel loadings by the components, the important fuel components that are out there. And the most important fire effect, of course, is smoke. And if we don't have accurate fuel loadings, we're never going to be able to predict smoke accurately. But there are many other applications beyond smoke and fire effects, is, you know, to inventory carbon stores for carbon budget models and so on, and to describe wildlife habitat and the coarse woody debris, and then to look at nutrient levels and understand how much nutrients and how productive the site will be in the future, and of course regeneration potential, and the list goes on and on and on. So all of these fuel loadings that you'll go out and sample or really have multiple uses now, rather than just to the fire effects models. I will say that after sampling fuels for 30 years, I can tell you easily that the biggest barrier we have to sampling fuels is their high variability across space and time. Fuel loadings are highly variable across space. 1 hour fuel loadings differ in their spatial distribution than 10 hours, which differ from 100 hours and 1,000 hours and so on. And just for those of you who don't know, 1 hour is fuels that are less than a quarter inch, 10 hours of fuels that are quarter to one, and 100 hours of fuels that are 1 to 3 inches in diameter, and 1,000 hours are 3+ inches in diameter. So in each one of those downwoody fuel loadings, not only is the loading highly variable, but the particle density, the density of the actual fuel, of that woody fuel particle, changes, and it has a coefficient of variation of over 50%. So not only are fuels distributed in time, in space differently, their particle densities are different, and so on to all the physical characteristics that we need to understand and predict fire effects and fire behavior, such as surface area to volume ratio and mineral content and so on. So these are the biggest barriers that preclude us developing actual classifications of fuel, and really prevents us from getting accurate estimations of fuel loading. So how can we mitigate this high variability? How can we put out a sampling method that will actually make sure that we're sampling the fuels at the right spatial scales and at the right times? And in order to, if you look at all the ways we used to sample fuels, or we sample fuels, is they're really boiled down to 4 ways. Destructive methods, which go out and you clip and weigh, collect the fuel, bring them in the lab, dry them, weigh them, and that's the fuel loadings, as long as it's done on a fixed area of known size. Destructive sampling, of course, is not very applicable to monitoring techniques, and most of the time destructive sampling is used to just research applications. Another research application is to go out and actually measure the volumetric size of the fuels, like measure the diameters and lengths of the woody fuel particles, or measure how much, what the volume is of shrubs and herbs and so on. And what we found is these volumetric measurement, while it's extremely time consuming, it has a lot of error associated with not only measurement errors, but also scaling problems. The planar intercept we talked about pretty extensively. This was developed by Van Wagner and implemented by Brown way back in 1974. Still used today, a lot of the things, and the planar intercept has its problems, and mainly because fuels vary in 2 or 3 dimensions, and the planar intercept only really samples in 1 dimension, which means you never really get an accurate estimation of the spatial distribution of fuels. And lastly, photo series. Many of you are probably familiar with photo series, where you take the picture and you match it, the picture to what is out there in the field, and then each of that picture, the fuels were measured for it within that picture, and you use those fuel loadings when you match it in the field. Well, the problem is most photo series use planar intercept to get their fuels. The new photo series, however, they have sufficient, like Roger Ottmar's photo series that he's done on his website has more than adequate sampling methods, but the old photo series done before 1990 really did not sample the fuels correctly, and so they have limited application in most fuels. So let's talk about this brand new Photoload technique, and what this seminar is going to do is it's going to teach you how to do it really quickly. Of course, what we designed it so it could be taught in less than 4 hours, and then you could be using it in one day. And I will tell you right now is that the more you do it, the more accurate you get. The manual for Photoload sampling technique is this GTR 190 that's available on the Rocky Mountain Research Station's website. You can download it anytime you want. I've reprinted well over 2,000 copies, and they're all currently gone. So I have none left. I'm sorry I can't send you, but you can download them and have a printer print them or whatever. And all the photographic sequences I have are in this particular digital copy of the book. There are several other aids to the Photoload sampling technique that I'll present at the end of this talk. Okay, so exactly what is the Photoload technique? In a nutshell, it's you look down at the ground and you delineate out a space. In this case, it's a 1 meter by 1 meter space. And you look at the fuels inside it. And we're going to do one fuel loading at a time. And so with your eye, you have to discriminate between the 1 hour, which are these 1 hours of these small sticks, and these are the 10 hours, these large sticks, and this is 100 hour over here. So what you do is you look at the ground, and then what we've developed is a series of graduated loadings of downward looking photos that look like this. And you can see this photo has 0.1 kilograms per meter squared, 0.3 kilograms per meter squared, and 0.5. So you look at the loading on the ground, and you look at the loadings in these graduated photographs, and you pick the one that best corresponds to the loading that's there. And that is essentially what the Photoload sampling method is. It's that easy, it's that simple to use in the field, and it's very, very useful, especially in inventory and monitoring applications, because you can sample the fuel at whatever scale you want, from 1 meter squares to larger and scale upwards. Now, a lot of you are saying, well, this is just another visual sampling technique. I probably really don't believe it. I didn't believe it either at the first, but I will tell you this, is that this sampling method, if you use it and use it correctly, will give you more accurate fuel loadings than the planar intercept technique. At the end, I'll show you 3 papers that you can look at where we actually compared them, and you can see that this is easily superior to the planar intercept technique. So, one thing I want to harp on is that the Photoload technique only gives you loadings for the six major fuel components: the 3 fine woody components, the 1, the 10, the 100 hour, the coarse woody component, or the coarse woody debris, which is the 1,000 hour logs, the shrubs and herbs. What's missing is duff and litter. And duff and litter, of course, can't be done with visual photographs, because it's the depth of the duff and the depth of the litter that gives you the loading, and those aren't available or visual in a photograph. So you still have to do that with the old techniques. All the techniques are described in that manual. So what we're going to do now is we're going to go out, and the rest of the seminar is I'm going to tell you how you can go out and make your Photoload sampling technique very efficient and very accurate. And so let's go ahead, and the first one we're going to do is we're going to sample fine woody debris. And in this procedure, we're going to go out and put a plot frame of 1 meter by 1 meter down on the ground, and which will encapsulate the fuels. And we're going to look at those fuels. So, we open to our first fuel component page, which I think is page 11 in the manual. But here is what that page looks like in the manual. And you can see that we've got tons per acre and kilograms per square meter. Now, I've always thought that tons per acre is not a very smart measure of fuel, because no one knows what a ton of fuel looks like, and no one knows what a ton of fuel spread over an acre looks like. So I always use kilograms per square meter, because there's a visual check. You can always say, hey, does it look like it's more than 3 kilograms or whatever? And don't forget, the conversion factor is 2.2 to go from kilograms to pounds. So there's what the page looks like. So we're going to go ahead, we're going to open up the page, and we're going to go down that page, go upwards in loading. So we'll go from here, and we're going to go up in loading until we see, and don't forget in this photograph over here, we have 10 hours, which are the big ones, and 1 hour, and we're just doing the 1 hours. And we're going to go upwards until we get to where there's too much fuel in there. And that would happen right around at 0.3. So at 0.3 kilograms per meter, there's too much fuel. So we then know we're between 0.1 and 0.3. And then we visually estimate or extrapolate between the two, and we get out. So we see there's too much at 0.3, too little at 0.1. We're going to go, okay, it's just a little more than 0.1, so we're going to approximate 1.3. And of course, the real measured fuel loading is 1.12. Now, when we teach these at various workshops, and we've done over, I think, 20 or 30 of them by now, when we teach these at workshops, in this particular thing is that most of the people are within 0.02 kilograms or 20 grams. That is, to me, is always astounding, because there is no way that Brown's transects can actually get you to within the real loading value that quickly and that easily with a visual cue. So that, very easily is how we estimate fine woody debris. You go to the photo that has the more than what's in the field, comparing it to the actual frame, what's inside the frame. You back off and extrapolate between the two. So I hope everybody's got it. We can go on, and let's move to shrub and herb. In shrub and herb, there's one additional step to that. So we're going to delineate the sampling number. We're going to open up to the fuel component page, which is here, live shrub, grouse, whortleberry. And we're going to match the species type, and we're going to look at, as we go through here, we're going to look at the one that's too great. And in this one, it's probably this photo right here, or 0.7. 0.7, and so we're looking at somewhere between 0.7 and 0.5. We're going to say, okay, the conditions in here, these three shrubs look like they're about halfway between the two, so we're going to estimate at 0.6, right? But we're not finished there, because if you look up in the top left, or right, I'm sorry, you can see the height of the shrub layer is almost 18 centimeters. Whereas the height of this shrub layer over here is 40 centimeters. These shrubs are half a meter tall. So you have to adjust for the difference in height. Obviously, right, because higher height means higher volume, which means more loading. So you take the ratio of 40 by 18, which is 2.2, and in Photoloads, you can, what I often do is round up and say 40 divided by 20 is 2, and we just multiply 0.06 by 2, or 2.2 in this case, to get 0.13. So we estimate off the photos, adjust for height, and what is the true loading? If everybody has been doing along with me, the true loading is 0.15. And so here we are within 0.02 or 20 grams of the real loading, which is a very good estimate. And I hope everybody followed that. And that's how to do for shrub and herbs. There's photos for shrub and photos for herb. So we've done 5 of the 6 fuel loadings. Let's go to the last fuel loading, which are logs of coarse woody debris. In this photo over here, you can see this yellow rope, and believe it or not, it stretches back. You can't really see it very well, but it delineates 100 square meters. This is because logs do not vary at scales of 1 meter, right? They vary at much larger scales. And so we have to delineate an area of 100 square meters. And we're looking at the logs in here. And so we delineate an area of 100 square meters. We're looking at the logs in here, and we open up to the right page. In here in Photoload, we have logs that are 6 inches in diameter and logs that are 10 inches in diameter. And in this case, because it looks like the logs in the stand over here are 6 inches diameter, we're going to open up to the 6 inches in diameter section. Now, if you look at this, of course, logs in our photos over here are not really logs at all, are they? They are just cardboard tubes that have been painted brown. And what we did is we just, the 6-inch cardboard tubes painted brown, and we calculated what the loading would be if they were solid wood. And so these served as logs. We really couldn't work with logs, of course, because it's kind of impractical to bring logs and put them on the lawn and get the loadings that we wanted. So, but anyways, here's the logs. And what you do is you go down and look at the conditions in the field here and match it with the logs that are here. And you're probably somewhere between about 0.1. So we're the 0.1 kilogram per square meter is too much, and 0.8 is too little. So we're probably in the middle. So we put it at 0.9. And now instead of adjusting for height like we did in the shrub, we're going to adjust for diameter. And the estimated log diameters in the field are 20 centimeters. The Photoload diameter is 15 centimeters. Over here, you can see 15.2. But the problem with logs is that the volume or loading varies with the square of the diameter. Remember, is the loading is dependent by volume, and volume is calculated by the square of the diameter. So we must increase by the square of the diameter. So we square 220, it's 400. Square 15 is 225. We get a ratio that's 0.18. And we multiply 0.18 times 0.9 to get a new one, which is 1.62. And what's the real fuel loading? Around 2 kilograms per square meter. So you're still getting within 25%, but these estimates really aren't as good as the fine woody debris and shrub because, of course, we're looking at 100 square meters rather than just 1 square meter. And it ended up that after extensive testing, we found that most people just don't like that whole sampling or adjusting the sample by the square of the diameter. It just doesn't work. And when we watched and observed people, what they were really doing is they were actually estimating the length of the logs on the plot and matching it to the lengths of the log in the Photoload series. So what we did is we came up with a brand new method to do this. And this method turns out it's much more accurate than the photo series of the photo load technique. And it works out, it's scalable and everything. So this new method is the same thing. You delineate your area, and then inside you go in and you can estimate by eye, or you can measure the diameter that's out there. And you can do it by log, or you can do it for the whole 100 square meter thing. In this case, we're going to estimate the average diameter to be around 11 centimeters. And then we estimate with our eye the total length. And the total log length we estimate in this photo is around 12 meters. You can probably do that with your eye right now and note that it's a 10-meter square. So you take a look, and now what we've done in the Photoload thing is we developed tables that where we can come in and we can match the diameter over here at 10 centimeters and go down to 12 meters, and we can get 2.02 for our loading, right? 2.0, and so we're estimating, because we're a little off, 2.06, and of course the log loading in this photo was 2. So with this tabular method, we actually found out we're much better off to measure these logs than we were before. So this tabular method ends up being much more accurate and much more fun. And of course, if you want, you can measure each individual log, or you can do it as a whole. So it's scalable and it's everything. And people generally, almost always, 90% of the people use these tables. And that, in a nutshell, is the Photoload sampling. I think you're all certified to go out and sample fuel loadings, Photoloads, once you have the actual manual. So why would you use Photoload? Well, for one thing, they're quick and they're fast. You can do estimates, of Photoloads for all of the 6 components in less than 3 minutes. Whereas to do that with the brown transects would take you much, much longer. You also, as I mentioned, you're sampling at the appropriate scale, the scale at which the fuel varies in the landscape. And while it's more accurate than planar intercepts, it's still more than accurate. The only one that's more accurate is actually destructive sampling. We've also found through our 30 various training sessions that we've done is that people tend to pick it up very easily. And one thing that separates Photoloads from all others is that it includes all the fuels but duff and litter. Note that the planar intercept does not give you shrub and herbaceous loading. And more importantly, I've been harping on the entire thing, is that you have a visual key or a visual cue to what the loadings look like, which means that the more you use Photoloads, the better off you are in estimating not only visual without Photoloads, but you're better off to get more accurate fuel loadings as you use the technique. And last, Photoloads really integrates well with other sampling methods. If you want to go ahead and sample canopy fuels with a tree inventory, you can easily use a 10th acre plot and nest your Photoload 1 meter plots within that and so on. And you can actually measure the logs within that 10th acre. So it really integrates well with other sampling methods, unlike the Brown's transects, because the Brown's transects, you need to sample oftentimes on transects that are longer than the actual plot radius. The disadvantages, of course, is that there's a user bias, so it isn't fully repeatable, although I'm going to talk about how repeatable it can be in a minute. And the problem is, of course, is that it doesn't have photos for every shrub and herbaceous species that are out there. There are only 4, so you have to use these 4 surrogates. And it does not work everywhere. It does not work, for instance, in areas that have shrub layers that are greater than 6 feet or 2 meters. It does not work for, peat bogs and so on. So you have to modify it to do that. And Chris Stalling, one of our Photoload trainers, is working on a technique and on how to do Photoloads for other areas. Some of the other limitations of it is that Photoload, we had to use just 1 wood density, and it's the photos are all of freshly fallen sticks. And as everybody knows, when you actually look down at the ground, all those sticks are in different stages of decomposition. So oftentimes, we can't match the woody density correctly. Again, there are only 4 shrub and 4 herbaceous species. You need to actually include more for local applications, of which we have a method now in order to do that. There's no duff and litter components, but the manual says how to do it, how to easily integrate it with our particular method, and it may not work everywhere like slash piles, large shrub fields, and activity fuels. But I want to emphasize is that what researchers and managers are finding is that it's incredibly flexible, and you can use it for local conditions. You can use, in this case, it was used for masticated fuels in the picture. It's very scalable, which means that you can scale it and get estimates of loadings across a stand for individual plots and so on. It's very adaptable. You can add it to other inventories quite easily, and it's adjustable. And of course, the biggest thing is that since you don't disrupt the fuel bed, it ends up being a very good way to monitor changes in fuels as a consequence of a fuel treatment. So Photoload techniques have great strengths, but they are a few weaknesses. Okay, those papers I was talking about, there are 2 here. If you send me an email, I'm more than willing to send you these. I also have everything that's ever been written about Photoloads and all the pictures and everything. I have a cloud site that you can download all these from, and these papers are on that, and you can take a look at our estimation. And in these 2 particular publications, we found that easily Photoload does better than most of the other sampling techniques. And in order to put in or sample at the Photoload's level of accuracy, you would need over 1 kilometer of Brown's transects on a 400 square meter plot, which is almost impossible and very impractical. So given a slot of time, if you want to measure on a plot and you want to do everything in less than 30 meters, Photoload was better than all sampling methods, and expertise played a huge role. Now let's do a deep dive into that just a minute. And here we went out and did brought over 50 people in the field, and then each of them self-rated themselves into whether they were expert, intermediate, or novice. And here you can see that the novice had obviously less accuracy than the experts. But if you took the average of the novices, it was almost the right exact estimate. So one of those wisdom of crowds things is that even though the novice had a wide range of variability, their average was more or less the right loading. But notice that wide range, that huge error bar that's around the novice compared to the expert. And so what we found is that in order to get really good, and in order to have residuals that are less than 0.1 coulomb, which is only 100 grams, is that you really need to be an expert. And that meant that you had to do photoloads, and you had to do them a lot, and you had to key your eye and calibrate accordingly. So about 6 years ago, Violet Hawley developed this little visual training tool. And in this training tool, we have a bunch of pictures like this, where we have a thing on the ground and what the stand looked like and so on. And in that 1 by 1 meter plot, we have what the loadings are. So you can go back to this 1 meter by 1 meter plot, calibrate your eye, and see if you were right or wrong. And it allows you this. I think there's 200 photos in this visual guide, and it comes in quite handy. And people calibrate their eye before they go out in the field. And people have been giving this guide to their training staff, their fuel sampling people, and they go out and train and calibrate their eye, and it works very well. Okay, so one of the last things we're going to talk about is how to integrate Photoload sampling out in the field. And if we're going for a complete fuel inventory, this is how we suggest it. And of course, this can also be used for in FS-Veg. You can use FS-Veg procedures to get all the trees above 10 centimeters or whatever your breakpoint DBH is. And then in a subplot of 100 square meters, you do the Photoload table technique for all the logs within this 100 square meter. And then you have these 1 by 1 meter microplots at 4 points along the outside of the log. And of course, we're out here because we have these are the fuel bed is least disturbed at this part. It's more disturbed at the center. And 4 plots we found just gives you enough to get an accurate fuel loading. Now, this would be what we would prescribe to a manager. And in this, to get photoloads at the 1 meter for the 110, 100 shrub and herb and the logs at the 100 meter, it will take around 10 to 15 minutes, and probably less as you go. Now, if you are a researcher and want to use it, we suggest putting these 5 additional plots in to get you 9, and this will get you more than adequate estimation of variability across these microplots, and this would add another probably 10 minutes to your sampling. So there in a nutshell, and of course, the number of plots, the 400 square meter, that's a 10th acre, by the way. The number of plots you put in depends on what your stand looks like and so on. So I can't really tell you how many macro plots you should use, but this is probably, once you have the macro plots decided, this is how you should do the underneath. Now, recognize that in order to get the accuracy for photoloads, that if you want to use planar intercepts, you would have to put at least 20 50-meter transects in here. Okay, so again, here's the Cloud Vault site. I'm more than willing to share this to anybody who wants, where all the Photoload technique materials are. The user's guide is here. You can just Google Photoload technique on Google Scholar if you want. The training guide is also there, and we have a CD on how we develop the Photoloads if anybody wants to replicate our process in another place. I am retiring, but there is a Photoload team of Heather Hewitt at the University of Idaho and Chris Stalling here at the Rocky Mountain Station. Both of them have done extensive workshops and training materials at conferences, and they will come to your place and put on a training session for your field crews if you want them. All you have to do is get in touch with them. And then Chris Stalling, of course, is writing a booklet on how to develop photoloads quickly and easily for shrub and herb components for your particular areas. So it's incredibly easy and efficient to do. And one of the other things, the exciting things we're coming up with is we are developing a pictorial guide to key litter and duff bulk densities so that you can get accurate estimates of litter and duff. Many of you know that in order to get litter and duff loadings, you measure the depth of the litter and multiply it by the bulk density, which includes all the airspace in the litter layer and all the airspace in the duff layer. Well, the problem is that right now everybody uses the same bulk density, but it changes dramatically by vegetation type and by potential vegetation type and by ecosystem. So we're having a training guide or a guide that will allow you to pick the best litter and duff bulk densities. So with that, I'd like to end and entertain any questions. So in this half hour, I hope you are hopefully familiar with the Photoload technique and are willing to take it out. One last thing, I think Sig was going to mention this, but if you go on Google or Google Photoload video, there is a 30-minute video that Heather Hewitt has done, professionally done, that will go through everything I've done today, only with additional detail. So if you're at all interested, please go ahead and take a look at that video. Well, with that, Sig, I'll give it back to you and accept any questions. Thanks, everyone.
All right, thanks, Bob, for the informative presentation. We're going to go ahead and open it up for questions now. If you have a question, please type it into the question or the chat pane on the webinar control panel. And while I give folks just a second to think of any residual questions, I'll remind you that the Northern Rockies Fire Science Network frequently has webinars, workshops, and field trips that might be of interest to you. So see our website for more upcoming events if you're interested. And you can also look at past event resources for anything that you've missed on topics of interest. So, and I will go ahead and post all the links to the Photoload YouTube video and a recording of this webinar on our past event page for this webinar, and that will be sent to you in an email later today or tomorrow. Okay, so it looks like we have one question. This is in regards to activity fuels. And Bob, you mentioned that the technique is not suited for activity fuels. Why is the technique poorly suited for activity fuels? And are you working on any kind of adaptation to make it more useful for that application?
Yeah, good question. Is that it actually works for activity fuels and it works really well, but it turns out that if the activity fuels are too high, in other words, you can't see the ground, in other words, there's so many activity fuels that you can't see the ground, you really have to do some other method because, you know, photoloads have to have that visual cue, and if there's fuel hidden by fuel on top of it, it really doesn't work that well. So activity fuels, it'll work in as long as you can see the fuel and see the ground. I hope that clears up that. If you can't, if your fuel loadings are so great that they're a fuel piled on top of fuel and you can't see the ground, then I would strongly suggest you measure the depths. And there are bulk densities for down woody fuel that you can use and sample that fuel load. It's called the Hood and Woo method, where you can sample the woody fuel based on the depth and bulk density of it, just like you do the litter and duff. So if, of course, you do see the ground and you can do it, then Photoloads will work perfectly. Thank you.
All right, thanks, Bob. I don't see any other questions right now. I'll still give you guys a second if you would like to submit any more questions. Everyone must be impressed with the simplicity of this technique. But if you are closing out the webinar, just a reminder that a brief survey will pop up, and we would really appreciate your feedback and input. If you have any ideas for future webinars or any feedback for this webinar, you can throw that in the survey, or feel free to send me an email or give me a call at any time. So with that, I don't see any other questions. Thanks all for participating today. And thanks again, Bob, for taking the time to share your research and all your work with us. Have a great rest of your day, everybody. Thanks.
Thank you.